So we discussed the Doppler effect in the last slide, and the core rules that we came up with for the Doppler effect is that the frequency of a wave goes up if you move towards an observer. So what that means is a frequency that looks like this might transform itself into something that looks like this if you move towards an observer. Likewise, a frequency that looks like this might look like this if you move away from an observer. So these waves here being all bunched up correspond to an increase in frequency. These waves here being all stretched out correspond to a decrease in frequency. And you can make similar arguments for the wavelength of the wave too. You can see the wavelength is changing, but it's an equivalent argument, so we'll just stick with frequency. And the last bit about the Doppler effect is that the larger speed you have, the larger velocity you have, the larger the shift in f will be. So, for example, you might have a wave like this at its source, and if you move it so one speed towards an observer, the waves might suddenly look like that. But if you move at a different speed, again, towards the observer, the waves might look like this. And from these two diagrams here, I can clearly conclude here that V1 must be less than V2. In other words, this speed right here, although it is moving towards the observer and producing the Doppler effect, this must be the slower speed, and this must be the faster speed. And this is what we mean here by the V is sort of proportional to the frequency, or the change in the frequency is proportional to V, something like that. The slower the V, it does shift it relative to the original, but not as much if you move faster. And so with that, here's how they figured out what the rotation of Mercury is. So here's Mercury right here, way, way, way over by the sun. Here's the sun right here, happily spinning away with that very slow rotation, 59 days, whatever. Let's say it's spinning like this. What astronomers did all the way down here on Earth is they have a big telescope, the Arecibo telescope, and I will show you some slides about that in a minute. It's basically a big parabolic bowl like this. And what they did is they shot waves at Mercury. Now, this is harmless. Didn't hurt Mercury or anything like that. And they were sort of microwaves even. So it's a type of radio wave that just happens to correspond to microwave. So they pressed a button, and these waves just traveled all the way to the solar system up to Mercury. Something like this. And eventually they encountered Mercury like that. So what these are here are, let's just say, Earth to Mercury waves, okay? And just for the technically minded here, they were microwaves, okay? So off they go. Now, here's where your Doppler effect comes in that we discussed. If you look very carefully at Mercury, the way the waves here would see it, you can kind of divide Mercury up into two parts, can't you? You can sort of divide up into two parts right through the center line like this and say, okay, everything over here is sort of moving away from the Earth, right? Because Mercury is rotating, say this pointer. They're all rotating sort of away from the Earth. Again, Mercury is just rotating like this, no big deal. But like if you were a little point, like a rock or a crater or something like right there on Mercury, you would be moving in the direction of this arrow here, and this arrow is sort of taking you away from the sound waves, away from the microwaves that are getting shot up by the astronomers. So generally speaking, in this region right here, Mercury is sort of moving up the direction of this arrow here, away from the sound waves. And what does that mean on the other side of this imaginary line I've drawn here? Well, I think you've guessed it, or you can guess it. If you're a little particle over here and you're rotating down like this, everywhere on this side of Mercury is toward the waves. So you see, you have a scenario which is ripe for the Doppler effect. You have half of the planet moving away from the waves, another half of the planet moving towards the waves, and then what happens then ultimately then as the waves then collide, boom, they sort of collide with Mercury, what happens is waves that hit on this side of Mercury right here, since things are traveling away, think of what happens to their frequency. Does it get higher or does it get lower? This section of the frequency is traveling away from Mercury. Well, if you guessed lower, you are right about that. So the waves that are going to go back to Earth, let me choose this pink color here, are going to look like this, and this, and this, and this, and this. And what I'm trying to draw here, this is a larger is a lower frequency because the Doppler shift is sending the waves off of an object that's moving away from the source, so lower frequency. How about over here towards? Well, it's going to be a higher frequency. So let me draw those maybe in a color like in white here. On this side, the frequencies are going to look like this. The waves going back are going to look like this. And what I'm trying to draw here between these two things here, this is a higher frequency. Higher frequency between these wave crests right here, which could be the wavelengths. It's definitely higher. Higher frequency. And so what the astronomers got back on the other side was two waves. They sent wave of one frequency out. That's the gray ones going out, but they got two coming back. They got some waves that were Doppler shifted to lower frequencies and other waves that were Doppler shifted to higher frequencies. And remember, as we said also last time, the frequency shift, the delta F, is related to the speed. So what they did very cleverly is they measured just how much these wave frequencies were shifted by, either in the away sense or the towards sense. They could use either one they want. And from that, they could determine Mercury's rotation speed. So what they got back on it was a graph that sort of looked like this. Here's the frequency, and here's sort of like the power. Believe it or not, yes, microwaves reflected all the way across the solar system. And let me just move this F down just a little bit, maybe to here. I'll say here, they definitely sent out an F naught, F for original, and so they got a lot of power going out. But what they got coming back also was, say, F1 right here, and sort of an F2 right here, where you can see that F1 is greater than F naught and F2 is less than F naught. So the F naught that is bigger, the higher frequency, well, that's going to correspond to, F1 over here, that's going to correspond to the Doppler effect back towards the Earth, and the F2 that's less, well, that's going to occur for the waves that had the Doppler effect for the side of Mercury that is rotating away from the Earth. So they got both of these frequencies back, and they could measure the shift in frequencies, and from that they could determine V, which is just how fast Mercury is rotating away from the waves on this side, or how fast it's rotating towards the waves on this side. So they had double data, dual amounts to get data to get both types, to calculate the speed in both ways, both do the Doppler shift towards and away, and that's how the rotation speed of Mercury was ultimately discovered, by bouncing microwaves off the planet and measuring the Doppler effect of the waves on return.